Hello, good evening. Today is April 23rd, 2022, and it's around 9:35 p.m. in Dallas, Texas, USA. And I'm recording this placeholder presentation because in about an hour and a half, I will be giving a distinguished lecture at the Vellore Institute of Technology in India. And that lecture will be at 9:30 a.m. Indian Standard Time, and that will be 11 p.m. Dallas, Texas time, and that's the US Central Daylight Time. I'm Bhavani Thuraisingam from the University of Texas at Dallas. And so now I'm going to share my screen. Okay, so my talk will take about just under an hour, but when I give this presentation live, I will give it sort of more slowly and also add some more information. So I will be talking, I think my talk is for about 2 hours, but my presentation will take around, likely around an hour and a half or so. And so this is sort of an abbreviated version, just in case there is a technology glitch. And so the title of my talk, by the way, I'm giving this talk virtually. The title of my talk is Integrating Machine Learning and Cybersecurity with Applications in Internet of Transportation and Infrastructures. And so this is my outline. It'll be in 3 parts. Part 1 is integrating cybersecurity with AI, machine learning, data science. And so it's a sample of the work that I'm doing. And I'm essentially using the words AI, machine learning, and data science interchangeably. And so I will be discussing big data security and privacy over our quantified self, and then data science, machine learning, AI for cybersecurity applications, and then securing data science, machine learning, AI. What happens if the machine learning techniques are attacked, right? So that's a problem. And then I'll talk a little bit about trustworthy machine learning. That's my current area of research. And then part 2 will be security and privacy for Internet of Things. In particular, I'll talk about Internet of Transportation and Infrastructures. And then part 3 will be applying part 1 to part 2, and that's security and AI for Internet of Transportation and Infrastructures. And I'd like to thank a number of our sponsors like National Science Foundation, Army, Navy, NASA, NIST, NSA, and my colleagues, Professors Alvaro Cardenas, Murad Kantajalu, Latifa Khan, and our former PhD student, Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, so part 1 is integrating cybersecurity and AI / machine / data science. So what's the motivation? Data science, security, and privacy. So I believe I introduced the idea back in 1996 about data mining applications and security, and in particular, the privacy problems that can occur due to data mining. I gave a keynote address at the IFIP 11.3 Data and Application Security and Privacy Conference in Como, Italy in 1996. And then later, I gave a version of the presentation at the Pacific Asia Knowledge Discovery and Database Conference in 1998 in Melbourne, Australia, and then published, I call it a landmark paper, I'll tell you why, a paper while I was at NSF that spawned a new area of research. I call it landmark because when you're a program director at National Science Foundation and when you publish a paper, then it's many people cite it because you are responsible for funding the research, and so it gets many citations. Anyway, a little later, around 2000, actually a little later after 1996, around 2000, researchers at IBM Almaden Research Center, they did some research, and they coined the term privacy preserving data mining. So the whole idea is, how do you carry out, maintain privacy, but at the same time carry out data mining, right, without violating the data privacy of the individual. So for instance, you want to find out the aggregate results, like people who live in a certain part of Texas have got, say, brain cancer, but you don't want to say that John Smith has got brain cancer. You want to protect that. So you have the original data, and then you add some noise like perturbation randomization. So noise is added, X prime, you modify the data mining process, but the final results have to be the same. So then I joined, I spent several years in the industry, around 24 years before I joined academia in 2004. And so my first PhD student was Dr. Li Liu, and together with Dr. Murad Kantajlu, we were focused on privacy preserving data mining, and in particular privacy preserving decision trees with the perturbation method. And that was between 2005 and 2008. Then later in September 2014, we organized a workshop. So by then we had big data, right? Massive amounts of data. So data mining, security, and privacy exacerbated, right? Privacy issues exacerbated with big data and data science. So we hosted an NSF workshop in Dallas, and then I presented the results to the interagency working group in February 2015. And so here are some of the aspects that we focused on: big data management, security, and privacy. So there are many technological advances and novel applications. So we can now capture, process, analyze large amounts of data for a number of tasks, security tasks, as well as other tasks. So such tasks could be like user authentication, access control, anomaly detection, user monitoring, protection from insider threat, and so on, right? And so you can analyze lots of data, integrate the data on the web, and then you can identify connections and relationships among individuals that may in turn help with homeland protection, disease outbreaks, and so on. Collected data, so you're collecting lots of data, even if it's anonymized, right? You can remove the identifiers. So you get two records, you remove the identifiers and you put the records together and you can re-identify the individual, right? So that's a challenge. And so security tasks like authentication and access control, they require detailed information, especially when you have multi-factor authentication. You need what? Fingerprinting, facial recognition, user ID, password, all kinds of stuff. And this information, if it's misused or stolen, it can lead to privacy breaches. And so at the workshop, we focused on a number of aspects. How do you secure the data? What sort of access control models? How do you carry out privacy enhanced big data analytics? And then what about big data analytics for cybersecurity? And what happens when the machine learning techniques are attacked? So in this presentation, I'm not going to talk about access control models. I'll talk about privacy enhanced techniques, big data for cybersecurity, and secure machine learning. Okay, so privacy aware quantified self, right? Many of us, there are billions of users carrying mobile systems like smartphones and iPhones and so on, and lots of data being collected. Now, this data could be used for a good purpose. And so sociologists and psychologists, they started this movement called quantified self. And so collect all the personal data from wearable devices and smartphone applications, and then you analyze the data, and then you give guidance to the various users. So for instance, I love vanilla ice cream and milk chocolate. By the way, I don't keep any of it in the refrigerator because I could finish 1 gallon of vanilla ice cream within an hour. But let's say I have it and I open the refrigerator and try to take milk chocolates. Wouldn't it be great if my smartphone or even the refrigerator can tell me, no, you're not supposed to eat that, right? It's not good for you. So that's, so it can help us with our personal life habits. But imagine all of this data being collected. If this data is shared with, say, my insurance companies or maybe my employers, that could be disaster, right? The insurance company might think, oh, she likes sweets. And if I do get diabetes in the future, thank goodness I don't have diabetes, but say I get diabetes, they may not treat me, right? So as a result, right, the privacy is violated, but then this data is very helpful for the user for health benefits. So such data collection and sharing often is being carried out without the user's knowledge, and that could cause a lot of problems. And another thing is you can take, say, device monitoring blood glucose, and if they find, say, let's say I have got high blood glucose or diabetes or whatever, and then the insurance company can not only deny me coverage, but it can also deny coverage for my for my son and for my grandchildren, right? So we don't want that to happen. So data collected, right? So such privacy violations could easily get out of control, right? Data collectors could aggregate financial, health-related data with tweets, Facebook activity, and purchase patterns, and so on. To address these growing challenges, what do we need? We need, without a doubt, quantified self is important, but we need privacy-aware quantified self. And so what do? We developed a privacy-aware quantified self data management framework, but that is policy-based. So policy-based, privacy-aware data managed quantified self. So we are carrying our smartphones. So data collector, data storage, data analytics, data sharing, and the data is coming from health data, fitness data, location data, social media data, and so on. I just want to make sure that, just a second, that my, okay, I just wanted to make sure that my sound is okay, right, that I'm not muted. Anyway, because once before I had done this presentation and I was muted, and so nobody could hear me. I had to redo everything. Okay, so what we are saying is every step of the way, all this fitness data, social media, and so on, all this data being collected, right? And some data could be anonymized and through cloud and go to the cloud storage, encrypted, anonymized, and so on. But this is where our technology. So what we are saying is every step of the way, right, we apply policies. So policies will guide the data collection, data storage, data analytics, data sharing. Okay, so that is what we have been working on. And so here it is. This is our smartphone, cloud-based encrypted data stores. So what we are saying is policy-aware data collection, storage, access, analytics, learning, and sharing. Lots of data being collected. As I said, storage on the device will not be sufficient to store all the data. So some of the data will be encrypted, some may not, and stored in the cloud. And we access the cloud through services based on access control policies. Local applications running on the device will be given access to some of the collected data. When needed, these applications will be allowed to access some of the encrypted data stored in the cloud with some simple query interface. In some cases, the data may not be needed in fine-grained form any longer. Example, storing 20-year-old daily weighted data may not be necessary. If you're 20 years old, we don't need to weigh a 20-year-old every day. Even he or she eats a lot and puts on 5 pounds, it may not be so bad, right? Not so taxing to the heart. But if a 70-year-old or 80-year-old puts on 5 pounds overnight, then that could be very bad. Similarly, if a 20-year-old loses 5 pounds overnight, it's not so bad. But if a 70, 80-year-old loses that much weight, it's going to be really bad, because they say tennis players, after an intense tennis game, they lose about 5-6 kilograms. That's several pounds. And that's fine, because most of them are young. They are usually, under, it used to be like 30, but now they are playing till 40, but still it's not old. But if you are 70, 80 years old, and if you lose 6-7 kilograms, that's going to be a disaster, right? So in some cases, data may have to be deleted to preserve privacy. And the whole idea is, what does it mean for data to be deleted? You need policies, and you need audit policies to make sure that data has been deleted. It's not like going to the bank and storing our jewelry in a bank box and later going and taking the jewelry. The jewelry is gone. But you go and put your data in a cloud, and then you delete your data. You want the data deleted, but there could be remnants, right? It's not like jewelry. Once you take it, remove it, the object is gone, a physical object. So based on difference, okay, so we also can carry analytics, right, using services. So based on different scenarios, some data may be encrypted, some data may be sanitized, and so on. But the point here is policies have to guide the every process: collection, data collection, storage, analytics, and sharing. Okay, so that's the first part. That's not, I mean, the first topic, right? Privacy aware policy-based framework. The other area, integrating cybersecurity and data science, is what about data science? When I say data science, it's AI, machine learning for cybersecurity application. And so this is joint work with Professor Latifa Khan. And so, so what do we do here, right? Using past data to build a classification model, and then you predict the label of future instances using the model. And this also helps with decision making, right? So you build the model, and then you predict labels, helps decision making. Now you can ask the question, what is the big deal? We've been doing this for 25 years. The challenge is big data, data streams, continuous flow of data, because data is coming continuously, right? The concepts could be changing, right? One model does not fit all, because back in 25 years ago, when we did data mining, we would develop one model, right? For small amounts of data. But when data is coming continuously, the concepts are changing. So it's very common. Continuous flow, massive amounts of data. So concepts changing means today it'll say buy Microsoft shares, tomorrow buy Apple, next day buy Facebook, and then buy Amazon, then buy Google. So every day things are changing. So what did we do? We tested with network traffic data. We developed our models. We don't develop one model. We develop an ensemble of models, so collection of models. So as the data comes in, we develop models. And then when new data comes in, some of the old models may not be valid. Then we throw it away, right? Or it happens automatically. These models talk to each other, communicate, and decide which ones to throw away, right? So benign traffic is stored in a server. When the test data comes in, attack traffic, you block and quarantine. And ever so often, you've got to check the models and update the models. So you develop an ensemble of models. For the model update, you could have an expert analysis and labeling, or it can also be done automatically. So you can have human in the loop, or it could be automatic. Okay, so we applied this to insider threat. Several applications. One I'll be talking about. Insider threat is sort of bad people pretending to be good people. Like these bad folks come and pretend to be good, take all the secrets and give it to the enemy, carry out espionage. Similarly, bad processes. Pretending to be good. So it looks like a database process, an email process, an application process, but they are really malicious and they pretend to be good, right? So we designed and developed ensemble based, a collection of models, stream analytics or stream mining algorithms, because these are data streams like sensor data and so on. So we had supervised algorithms and unsupervised algorithms. For supervised, we use support vector machine, traditional, and one class. We have also designed and developed unsupervised, so various techniques, including a compressed dictionary-based approach, a graph-based anomaly detection approach. In unsupervised learning, we do compression used to model common behavior to enhance its performance. This results in a classifier, and it exhibits substantial increase in classification accuracy. We actually found that unsupervised performed better than the supervised approach. Okay, so here is our architecture. So a person is typing all kinds of sequences, system calls, and so on. You have I chunks, you gather the data, you extract features, apply unsupervised like compression-based and graph-based methods, and then support vector machine-based methods. You build an ensemble of models. As new data comes in, you throw away, some models are outdated, you throw away the models and so on, and put in new models. When the I+1th chunk comes in, you extract features and then you test train, and is it anomaly or not? So a lot of the techniques are more or less the same, but the challenge is massive amounts of data, streaming data, and building this collection of models, ensemble of models, and throwing away the bad models. That's the research that we have contributed to. Okay, now, what happens if these machine learning techniques are attacked? We are applying machine learning not just for cybersecurity. As I mentioned in my previous charts, we are applying machine learning for healthcare, for finance, for retail, for marketing, for practical medicine, for practically for IoT, every application, autonomous vehicles. So machine learning is being applied. What happens if these machine learning techniques are attacked? Right? For healthcare, if it is attacked, it could say, oh, you just have a cold. But in reality, you could have COVID, and in time you could die. So that's the challenge if it gives you wrong results. So adversary is trying to learn about what we are doing, right? And so it's trying to change our data. It's trying to change our models. So we have to understand how the adversary is learning, and we have to counter that. It's not concept drift like I mentioned earlier. It's not like online learning. Adversary adapts to avoid being detected. And that could happen during training time. It could happen like data poisoning. It could happen during testing time, modify features when data mining is deployed. So a game is being played between the data miner and the adversary. So look what happens. The red squares are bad instances and the blue circles are good instances. But look what the adversary is trying to do. Because if it comes, this is a support vector machine boundary. Anything below the boundary, in this particular case, we are assuming bad, good, and above the boundary is bad. So adversary will try and learn what the model is and try to push the red squares into this below the boundary. See what happens. So now 1, 2, 3, 4, 5 red instances will be considered to be good instances while they are bad. So even if one bad instance pretends to be good, some great damage could be done. And so what did we do? First of all, before we discuss a solution, we've got to understand the type of attacks. So we have we looked at 2 classes of attacks. Free range attack, where adversary can move the malicious data anywhere in this domain, right? We have a lower bound, we have an upper bound, and you can move the data anywhere. And a paper, the KDD paper that I mentioned, in the next chart, I'll show you. And the other is targeted attacks, right? So I don't have the time to sort of explain all the math. It's just that there is a minimum lower bound and an upper bound, and the adversary can move the data anywhere. Targeted data, adversary can move the malicious data closer to the target point. So here we have, this is the original support, the dash line is, the black dash line is a standard or the original support vector machine boundary. And so here we are saying we are just a little bit different in the sense we assume that everything above this boundary, good instances, here below, red crosses are bad, green circles are good. So we do all the math and then we try to figure out where to move this boundary, right? The blue line is the adversarial support vector machine. So we try to move the boundary to this blue line. And by moving it to the blue line, remember, before that, when the line was here, there were some crosses which had crossed over and they would be considered to be good instances. But by moving the boundary, right, some of these red crosses below the boundary are now will be caught, right? But unfortunately, some of the green circles also will be coming across as bad instances. And I'll explain that. So this picture is a little bit more clearer. So the red crosses, the green circles, and then the black sort of crosses or stars or whatever, they are the bad instances that are being pushed to be good because we have moved the blue line. So by moving this blue line, some of the bad instances are caught, right? So that's what we do. So we do the math and see where do we want to move the blue line. Of course, you can say we can move the blue line here. If we move the blue line here, then what happens is that all the bad instances will be caught, which is great, but all the good instances will be called bad instances. You see? So that's the challenge that we have, the correct place to move this boundary. Okay, so another area that is really becoming very important these days is trustworthy analytics, right? So here I'm only talking about, I just finished a paper for IEEE Intelligence Systems where I explained the complete picture, what trustworthy analytics. So computations over big data require massive amounts of computational resources, and you may have to use third-party services, and whenever you use third-party services, right, there could be man-in-the-middle attacks. You cannot trust everything, all the services. So some of the computations, you cannot trust, and adversaries, there could be adversarial threats. So what we are saying is we need machine learning to be secure. And one way we talked about security is this year, right? Playing games and trying to modify the support vector machine line. Another way we can secure is maybe use hardware, such as I'll show you the next chart, Intel's SGX, right? Intel SGX. Platform and execute the machine learning software in hardware in protected domains. And that way you can provide some sort of security. And there's also a lot of work, especially at Oxford University in the UK. They are doing a lot of work on applying logics for machine learning, for formal verification, for specifying for specifications of the machine learning software and then formally verify. So trustworthy machine learning, I just wanted to mention, which I don't have in the chart, it's not just security. Trustworthy machine learning goes beyond security. It's not just secure machine learning. You need the machine learning algorithms to ensure privacy. You need machine learning algorithms to be correct, not give wrong results, even through false, so integrity, and also fairness, because machine learning algorithms could be biased because the humans are biased. Because when you go to give bank loans, right, usually they give bank loans to maybe men. It may discriminate against women or against minority, underrepresented minority groups, because we don't have enough data, since most of the loans are being given to certain groups of people. And so if there's human bias, that bias is transformed into the machine learning algorithms, and the machine learning algorithms could be biased as well. And so mortgages and bank loans, and also prison, lawyers, judges, giving prison sentences may discriminate unfairly, say, against women and underrepresented minority groups. And so fairness in machine learning is also part of trustworthy machine learning. I just wanted to mention that. So I just wanted to talk about the SGX. So we have done a lot of work in executing our machine learning algorithms in the SGX platform. So the platform has got, a number of things like runtime library and wrappers and encrypted code and so on, but they have got this enclave memory, secure trustworthy locations, and that's where you are executing these machine learning algorithms. Okay, right. So that finishes part one. Now we move on to part two, which is another topic, and then I want to combine both together. So part two is security and privacy for Internet of Transportation and critical infrastructures. Okay, so Internet of Transportation, we know Internet of Things right here. In your house environment, you've got your coffee maker, tea maker, connected to your clock, connected to your microwave, with your television, with your emails, with your Wi-Fi, and all of these with your, let's see, your cell phones and Amazon purchasing and everything, all connected, and they're talking to each other, right? The things are talking to each other, sensor data. Similarly, there's Internet of Things for medical, Internet of medical things, your heart monitor talking to your, what else? I mean, your pacemakers talking to your all the electronic gadgets you may have in your body. So that's Internet of medical things, Internet of financial things. So we have Internet of transportation things like cars talking to trucks, talking to roadworks, talking to trains, and so on. So Internet of transportation, major implications in the transportation industry, autonomous vehicles, right? We are migrating towards driverless vehicles, improving day-to-day activities, like in the US, right? Trucks are carrying 63.3% of the freight of goods. Autonomous vehicles not limited to ground vehicles, but also include aerial and sea vehicles with a wide range of applications. So for example, we found that the level of automation for autonomous vehicles range from 0 to 5, and current ground vehicles in the market have partial automation at level 2. Aerial vehicles have got higher automation, like level 4. Companies are investing heavily in autonomous vehicles, like GM spent $720 million in 2018, over $1 billion in 2019, and I've got to get the numbers for 2020, and now we also need numbers for 2021. I'm sure it's well over $1 billion. While there's great potential, what's the big challenge? Security, and there's also privacy, but security is crucial, because what happens to all these transportation systems, right, all talking to each other, and they are attacked. And so there could be chaotic situation. You could have all kinds of accidents, right? It can maliciously ask everyone to take a particular route, and you take that particular route. It's so congested, it's going to take you hours and hours, right? So very chaotic things could happen. So security for autonomous vehicles is very, very different, because it's sensor data. It's not like network traffic data. So AVs evaluate their environment using a variety of sensors like camera, GPS, inertial measurement units, LIDAR, radar, ultrasonic sensors. Previous research has shown sensors are susceptible to malicious tampering, like IMUs are susceptible to sound waves, and GPS receptors are susceptible to spoofing signals. So vehicles should verify the veracity of sensor signals before acting upon them, right? So you have sensor-based, so AVs rely on sensors to evaluate and interact with their environment. Inherited issues, sensors are susceptible to GPS, spoofing that we have done some research and others have done research and found, and transaction attacks that manipulate environmental, physical science, visual, sound, magnetic, and so on. That's the inherited, and then inherited because of the particular type of environment. Needed defenses, classical computing security such as memory protection and cryptography, because you don't have the time and the limit because they are energy constraints, right? So they are tiny devices, they got storage, they got energy problems, so you don't have all the time to do memory protection, cryptography, authentication, and so on, right? So you can't really, you may not have centralized party, a central third party to do all the verifications, because it's very hard. So these autonomous things, right, these vehicles, they have to sort of talk to each other and maybe verify and validate each other. So I just finished teaching. Yesterday was Friday was the last day I taught my Internet of Developing and Securing the Cloud, Edge, and IoT. And so, you know, we talked about various types of attacks to IoT systems. So Internet of Transportation is one aspect of IoT. And verification, because there are real-time constraints. It has to be very quick. There's not enough storage. And so AVs trust and act upon sensor data, and there's not really much formal verification. You might need special verification techniques. So what did we do? So we built a physics-based, that means based on the physical model of the cyber-physical system. There's a cyber part, there is a physical part, right? Physical part depending whether it's a car or a plane or a ship, right? So we have to build a model based on the physics, and the algorithm has got three parts. You build a model offline using the physical invariants, implementing an online tool to monitor and expected and observed behavior to detect the anomalies. And then you raise an alarm, right? If there's a significant residual difference between the executions, offline pre-processing, online verification, anomaly detection. So you could ask, so what's the big deal? We've been doing that all the time, right? Challenge is coming up with a model. And so my colleague, Dr. Cardenas, is a top expert in control systems and securities. So my contribution was more on the security side. So he and the student built a model. So offline pre-processing, AV's invariants are calculated using well-known nonlinear models for aerial and ground vehicles, accelerometer, gyroscope, and magnetometer. Sensor data on the X, Y, and Z axis is used for, or Z axis is used for the aerial vehicle. Vehicle position and steering angle is used for the ground vehicle. So like, for instance, K is state and Y is input sensor signal. Y tilde is a pre-processed sensor reading. Like LX, LY, LZ, or LZ, moments of inertia needed for the nonlinear equations. M is mass, D is drag factor, B is thrust. So this is the model. Online, we are using Kalman filter. We didn't use any fancy machine learning for this particular work. So we use extended Kalman filter that electrical control systems engineers have been using it for a very long time to predict the AV's physical behavior. And then you estimate the unknown parameters from the noisy sensor input. And the algorithm is divided into two sections. One is to predict and correct the estimation before it is compared against the sensor data. And then anomaly detection, a CUSUM, a CUSUM algorithm, it's a statistical approach, is used to detect persistent attacks. And then you raise an alarm if the residual difference is larger than a predefined threshold. Okay, so how did we implement it? We did it implemented for drones, that is air, right? We didn't have airplanes, of course, drones is air vehicles. And then for cars, we didn't do ships, right, or boats. So aerial Intel ready to fly RTF drone, controller is a PX4 flight controller focusing on detecting, remember, aerial is GPS spoofing and gyroscope attacks. GPS attacks we detected after 0.2 seconds, while gyroscope attacks are detected after 1.5 seconds. The overhead introduced was 5.4332%. The ground AV, we had a custom built on top of Traxxas Ford Fiesta, right? Chassis controller was ROS kinetic cam, focused on detecting visual attacks on the camera, right? Because remember, we said earlier, prior research has shown that camera has got visual attacks detected after 0.1 second, and the overhead was actually less, 2.25. And each threshold produces a probability of false alarms of approximately 2%. So you could think that false alarm of 2% is small, but no, that would have been okay 10, 15 years ago. Today, they are expecting, right? You need false alarms and false positives, false negatives like 0.000002, very tiny, right? Because with today's technology, 20 years ago, maybe 10%, 15% may have been okay because with that technology. But today, so that's why we are now looking into machine learning for this particular project. Okay, so what about privacy? So we haven't really spent as much time on privacy for this application. I'll talk about what we are planning to do, but privacy is important because beyond the security of individual vehicles, the transportation sector could greatly benefit from supporting infrastructure that allows communication between vehicles, motion sensors, lampposts. Without a doubt, machine learning is very important for transportation, right? Because giving us the correct routes and what to avoid, and there is an accident or accident is going to happen, emergency alerts, all great stuff. But because we are applying so much technology from a user's perspective, privacy concerns arise from all the information that's being gathered, right? So for instance, if I'm smoking in my car, I may not want someone to take a photograph and send that to my insurance company, or all of the private information. I don't want people to learn about my driving patterns if I'm not a good driver and send that to my insurance company. Or I may not want people to know where I am, a particular location. And if the location doesn't have privacy, then that could also violate my privacy. And so while security is crucial, privacy is also important. That's why legislators, engineers, scientists should keep privacy in mind when they are designing these autonomous vehicles, right? This will aid at improving public perception, reduce hesitations, and so on. And also adopt new technologies. If I know that the technology is providing some aspect of privacy, then I will be more willing to adopt that technology. Okay, so now we go to the last part. Applications of security and AI for Internet of Transportation and infrastructures. So one, data science for transportation security, right? So without a doubt, Internet of Transportation subject to attack, right? Physical attacks, cyber physical systems. It could be the power grid, we said autonomous vehicles, so any type of cyber physical system. Streaming data is being collected because sensor data is in a way streaming data. And in the future, we will have driverless vehicles, right? And as systems go electric, we also need energy conservation. So threats to the security of such systems could cause massive damage, right? We could loss of lives, we could get stranded on highways, and we can manipulate all the fuel gauge and various other things could be manipulated. So we are looking at data science ML techniques, just like we applied for the network traffic data. Can stream analytics be applied that we are applying for, say, financial data, and telecom data be applied to transportation data? Second, the main question is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensor data being collected. Okay, adversarial machine learning. Remember, these machine learning techniques could be attacked. So Internet of Transportation, without a doubt, heavily depending on machine learning, right? More and more car companies and airline companies and so on are applying machine learning for a variety of applications because they are providing a lot of benefits, right? And you want to drive without the human in the loop, without a doubt, you need machine learning. But the adversary is not going to keep quiet, right? So the more technology we are using, more machine learning, adversary is watching. It's trying to look at our data, the vehicle's data, and then trying to thwart the vehicle's data from learning, right? Or learning wrong stuff. Adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms have to adapt, and we have to thwart the adversary's actions. Eventually, it becomes game playing between us and the adversary, and the vehicle and the adversary. And the challenge, what sort of game will be played? Zero-sum game, Bayesian game, Stackelberg game. So research is just beginning on this topic for autonomous vehicles. And then remember privacy. So remember the earlier picture I showed with our smartphones, iPhones, with data collection. So there we had social media data, healthcare data, and so on. Instead, we have a little gadget here, like a smartphone, a little gadget in the car. And there's data collection, data storage, data analytics, data sharing. But the data here is radar, GPS, cameras, LIDAR, ultrasonic sensors. and then some of the data anonymized and encrypted and in the cloud. And IoT systems, right? IoT systems, if you look at it, they are at the edge. There's all the things, right? Internet of Things. Near them, there is these edge nodes. And then you have the fog, right? Collection of edges together is a fog, more like a local area network, a little bit of a computing, more computing power. Eventually, everything is sent to the cloud for further analytics, right? So that's what I'm saying here. So some of the data could be in the cloud-based, through cloud, stored in the cloud, encrypted and anonymized, and through cloud services. The question is, can we come up with a privacy-aware, policy-based data management framework for Internet of Transportation system? Okay, my last chart, one before the last, directions, developments in integrating cybersecurity and AI. Without a doubt, data science, ML, it's exploding. Practically every application. Applications of AI for security, insider threat detection, and security for AI, adversarial machine learning, okay? Developments in privacy-aware healthcare, managing one life's activities, right? Privacy-aware quantified self. At the same time, with Internet of Things and Internet of Transportation, Internet of Medical Things, financial things, security and privacy solutions are being developed, especially for cyber-physical, Internet of Transportation, physics-based solutions. You model use physics to model the the physical part, and then you apply the cyber. As driverless cars become a reality, more and more of the AVs will be used for AI ML techniques. How can we develop AI solutions for detecting malware in AV systems? And how can adversarial machine learning work in AV systems, right? So that's something, questions, our current research. And then can we develop a privacy-aware policy-based data management framework for Internet of Transportation and infrastructures? And finally, is it possible to perform trustworthy machine learning, right? When so much of data is coming from all directions, formal methods, Intel chip. And when we say trustworthy, it's not just security, it's also privacy, it is integrity, it's fairness, it's fault tolerance, everything together. So it's just a huge problem. And so numerous opportunities for substantial research and development. So whatever I have discussed, I mean, you could produce probably 10, 20 PhD theses out of this. And that's why I talk about this topic at several venues to motivate the students to conduct research in this area. And my last chart, of course, I'd like to thank, as I said, my colleagues, Professors Alvaro Cardenas, Murar Cantarjalo, Latifa Khan, a former PhD student, Dr. Raul Quanenas, and also Ms. Rhonda Walls, our project coordinator. Okay, so now I'm going to stop sharing. Okay, and so this finishes my presentation. I believe I sort of rushed this a little bit because although I've got 2 hours for my live presentation, but I can, I sort of talked for about 45 minutes. But if I go slowly, right, this particular presentation will take about 1 hour and 15 minutes or so. Or maybe even 1 hour and 20 minutes, and then I'll be there to answer questions. So I guess I will see you all in about 20, 25 minutes. And again, thank you very much for inviting me to give this distinguished lecture. And hopefully sometime soon. I've heard so much about Vellore. I've been to Chennai quite a few times and to other parts of India, but I've not been to Vellore, and I've heard so much about Vellore. And so hopefully sometime in the near future, we can all meet in person. You can come to Dallas, or I can come to Vellore, and we can have, I'll be happy to give some lectures there. And so, so anyway, again, thank you very much, and I will see you shortly. Okay, thank you. Bye.